All right, let's now talk about polar graphs. In this video and in this class, I'm not going to focus a lot of time spent on sketching polar graphs by hand, but I think it's very important moving forward that you understand where polar graphs come from. And if you had to sketch them or to describe a polar graph, you absolutely could. So what we're first going to do is talk about this example. I'll get a little bit deep. I'm not going to do a lot of physical work to do this, but describe where this graph comes from. And then I'll go through all of the general types of graph you'll see and their form. So again, first I'm going to get a little deep with this and then we'll generalize. I'll show you a bunch of just different graphs and their general forms in polar coordinates. First and foremost right here, I think the absolute best way to think about graphing polar coordinates quickly is to view the rectangular coordinate relationship described by this equation right here. So first and foremost, let's look at a graph of this where I'm treating r as my y value and theta as my x value. And importantly to say to this is that you don't have to get any deeper than 0 to 2 pi when you're thinking about this, because that's all the range of values that will be output. You have your full graph from 0 to 2 pi. That wouldn't be true if you had some coefficient on your theta. Like if it was 1/2 or theta over 2 right there, you'd actually have to go to 4 pi to create the whole figure. But we're not going to be considering those kind of graphs in this conversation. So we look at this graph right here. And what I want to do then right now is look at this in the polar coordinate system right here. So this equation describes this graph right here. And my point being here, and again, I think this is the most powerful way to graph these things. By the way, this is called a limison, this little figure that's got a circle with a little blip on the inside right there. By the way, they're the coolest when this value is bigger than this value right here. If that value is bigger, they don't have the little loop on the inside. I'll talk about that a little more in a second. But the question is, where does this figure come from given this image right here? And importantly that you can see right here, well, we have this little part of this because the amplitude of cosine, so this is an amplitude and this is a shift up. So we have 4 cosine, which has the amplitude of 4, but we've moved it up to 2, which means we have just this little blip right here that's under the x-axis. That's the little loop on the inside right here, because between those range of values right there, when it goes underneath the x-axis, I'm going to get negative r values, which make it go in exactly the opposite direction. So importantly, when you see the end of that little blip, and it's not really called a blip, I'm just calling it a blip, right? But when you see the end of that r value was actually negative and it was pointing in 180 degrees the opposite direction, but the negative r value made it go in that way. And then this isn't a really scientific way of doing this, but for me, visually, this really helps in seeing these graphs. If you took this figure right here, you took the x-axis from 0 to 2 pi and you wrapped the 0 and the 2 pi together, so you had this figure, now you have this circle, that the x-axis is now this circle. You're getting close to that. Then what you would do with that x-axis is you take like a zip tie or something like that, and you pull it so the x-axis, that circle from 0 to pi, goes into one origin point. And hopefully you can see that as you would do something like that, you would get this figure. Okay, so we're quickly just going to run through some polar curves to end this video. And it's not expected that you've memorized all of these, but the hope is you do have a little bit of an understanding where they came from, given the examples we've already seen, and just your understanding of polar coordinates. First of all, if you're giving something that is theta equals k, so this is a constant, these two cases I have right here are like y equals 5, or a constant, and then x equals a constant, right? So in this first example right here, if I were to graph theta equals pi over 4. What this is, it's all of the points that have an angle of theta, but given the range of y values, right? And so in that case right there, what we have is a straight line that has an angle of pi over 4. So this right here is a line. So when theta equals a value, we get that at that angle, and we have a straight line given all r values. And the same thing here, this is the graph that has a fixed radius, but every theta value, and what that would be is a circle of, so let's say r equals 5, as I said right here. And what that is, it's a circle of radius 5. And importantly here also is that this circle with this kind of equation is centered at the origin. So let's run through some other forms. I'll give you the general forms here, but we'll use Desmos to give you a beautiful graphical version of what we're talking about. First up, we have polar equations of the form r equals a cosine theta plus b sine theta. A and b throughout all these explanations, just arbitrary constant values. This will output a circle. We actually know that right over here. We've already seen that and described that. But importantly, these are circles. And also to say is that you can think about any a or b being 0. And if you had something like a cosine of theta, this is a circle that's actually, it's centered on the x-axis. And if you have r equals, we'll just say b sine of theta right here, this would be a circle centered on the y-axis. And then if neither a or b are 0, then what you get is this circle that's not centered on one of the axes. And then if you have these linear equations, so r equals a plus b theta right here, beautifully, for some reason I just love r equals theta, the equation right here. What we get in this case, these linear equations in polar coordinates, are these beautiful spirals. So then we have polar equations of this type right here, where we have a 1 plus or minus the cosine, or a times 1 plus or minus the sine. In this example, you can see right here, this figure is called a cardioid. And just to me, it's kind of interesting to look at this and to think, why, if I have a 4 right here, why when I'm at 3 pi over 2, why does that output an 8, or a radius of 8, and why does it have that shape? And the same reason, why at pi over 2 do I have a radius of 0? And given when you're thinking about this, if you're thinking about either of those real quick, is just say, you can quickly kind of think about the orientation of the ones that have sine versus the ones that have cosine. And then we have these figures right here. We've actually already seen this and talked about this. I'm a little excited about these. These are called Limisons. And again, we talked a little bit why it has the shape that it has with this little blip on the inside right here. Importantly, I want to say, so this is the equation for these Limisons right here. But in my mind, these are only interesting if the b value is bigger than the a. Just to give you 1 second, let's switch these around and let's look at what happens if this is 4 and that's 2. And I think you probably can agree that's not quite as cool. Importantly to think about, and go back to our previous conversation just briefly, is while this is still a limison, it doesn't have that little loop curl on the inside. Because this right here, this translation up on the x-axis, if you think about this in the rectangular form like we had, this is too big for this amplitude to reach below the axis to get that little blip right there. So the little kind of flat part that you see right there is this going down, but it never reaches underneath the x-axis, so we don't get that little curly part on the inside. And then finally, we have our last polar graphs, which are roses. Our roses are described by these equations right here. And importantly, what's going on that's different than our other examples is this period change right here with this b value. So we're speeding things up. As we go around with our angle, we're actually, this outputs things quicker than it does on the general unit circle. And importantly, 2 things happen. First of all, probably one of the coolest figures you'll ever see right here. But importantly to say is this, if you look at this as r times 2 cosine of 2 theta, if this coefficient on the inside, so in the argument or on the theta right here, if that is even, you will always end up with a rose with double the number of petals. So we'll always have twice the number of petals as that coefficient on the inside. But if we have an odd number of petals, we don't end up with twice the number of petals. We just have 3 petals in that case. And so importantly then also, if b is odd, all we have are b petals. All right, and lastly, I'm resisting the urge a little bit to talk about why the difference between these two, and I won't go into depth, but I do want to speak a little bit about it and to say, if you were interested and wanted to investigate this, you could play around with different b values and look at the rectangular coordinate version of that graph. And then what happens is you would realize, well, they should always have twice the number of petals, given how this graph does. And again, this b affects the periodic nature of sine and cosine. I think about the multiplicative nature of b as it speeds up sine and cosine, which means it shrinks the actual period of those functions. But to say you should have double every time, but if your B value that you're using is odd, what happens is petals get doubled up on the way. So instead of having 6, what we do is as we go from 0 to 2 pi, we trace those 3 petals twice.